All right, friends and neighbors, welcome back. Welcome back. We are going to talk about something a little bit different, but certainly part of our world, no matter if you were talking about networking or application development or communication flow. So we are going to chat about buffer thingies. Now, first up, I suppose we ought to define exactly what a buffer is. So whenever you, at least this is what I do in my brain, whenever I think about the term buffer, or in my case, more often it's queues, I think about memory. So our friends out at the Telecommunications Industries Association define a buffer this way: a routine or storage medium used to compensate for a difference in the rate of flow of data or time of occurrence of events when transferring data from one device to another. So that is a telecom definition. But if we expand that a little bit and we just think about memory and we think about all the places that we're moving data or instructions or addressing into and out of memory. This happens inside a computer when you're moving things from a hard drive. It happens inside a computer when you're moving things in and out of RAM. And inside a computer, there are actually a whole bunch of different kinds of memory. And so we have to move data around all the time. When it's flowing across a network, it goes into a router and then out of a router. But if we drill down a little bit, it goes into a particular interface, and that interface has memory. And memory is allocated in both the incoming and the outgoing directions. And every single port has that. So we have memory all over the place. And a buffer is used to handle variations or problems associated with moving data around. Now, the reason I specifically mentioned data addressing or instruction is because we have the Van Neumann model, and that is the architecture that we still use today in many, many places, where inside a computer you have the bus, and the bus is consistent of communication lines for addressing data and instruction. Now, of course, the related terms to this are queuing or queues, caching or caching, depending on how you like to pronounce it, and of course pointers that say, hey, there it is. So we talk about cache. Probably the most significant type of memory that we talk about in this category would be maybe L1, L2, L3, or level 1, level 2, level 3. And these are very, very fast, very, very expensive, and usually pretty small memory locations, and next to the CPU. So again, from Standards Online, there from the Telecommunications Industry Association. By the way, that's a free online telecom dictionary. You can just go to that website, put in the term that you like. It's a little limited because it's very telecom oriented, but there you go. Buffer, smaller and faster than main storage. So again, in a computer, you have your hard drive, whatever it is, SSD, rotational still, RAM, and then memory that's close to the processor. And these are your L1, L2, L3 sometimes. And on top of that, every time you put a card in your machine, it also has memory and it also has processing capability. So this is used to hold a copy of instructions and data in main storage that are likely to be needed next by the processor. So main storage here might be something that was moved into RAM, but it's outside of the cache, and then we move it into cache, and then it's acted on right away. Now this is not a computer architecture sort of chat, but if you want to, you can really take a look at registers and how data moves in and out of registers. Now the fun thing about cache memory, in addition to being fast and expensive and near the CPU, the fun thing about all of this architecture is that it really makes a difference where it is. And this is one of the reasons it's located very near the CPU, or sometimes attached to the CPU, or at least in the CPU stack where the CPU connects to the motherboard. So all of that stuff is part of that assembly, because there's actually a measurable time difference when we have to move stuff around, even on the motherboard. Now extend that to a network, and you've got massive delays, comparatively speaking, in moving data around. So what is a queue, right? We've probably all used the term, well, I'm in the queue, whether you're waiting on a telephone call, or you're on hold, or you're in line at Disneyland. So a queue is a set of items such as telephone calls or packets arranged in a sequence. Now, For a networking device, this means that we're talking about stuff that was traveling across the network, and let's think frames or packets. So they're arranged in sequence, they're traveling across the network. Now this is independent of a particular flow, right? As data is flowing from one side of a network to another, when it is released by a particular device, there are a whole bunch of these flowing across the same link at the same time. So they're sort of lined up in time, one behind each other. Now, when we get to a device, the queue is used to store events occurring at random times and to service them according to a prescribed discipline that may be fixed or adaptive. Okay, what is all that about? Your traffic is flowing across a network. And let's say that we're talking about 1,000,000 packets. So a router is receiving, say, 1,000,000 packets per second. Now they get to a particular interface, but they're moved into the input queue, and the router has to service that queue. So what do we mean by servicing? Well, there's a queuing strategy or a discipline that we use to service that queue. Probably the most common queuing strategy is FIFO, first in, first out. The first packet comes in, we figure out what to do with that, and we move it to the next queue, and then so on and so forth. But there are lots and lots of other queuing strategies, depending on what you're trying to do. Some users or some application flows might actually be prioritized, and so they either get more or less of the queue depending on the strategy. Now there's a screenshot here of a router serial queue, and we can see that there's a size defined and there's a strategy associated here. This is weighted fair queuing in this particular case. And so you can take a look at a busy device and see how many things are in the queue, the size, what is our maximum size, and then if we're dropping things, and make adjustments to your queuing strategy, or even adjustments to the device if you got to replace it, get something bigger and badder, or change the port, change the module, etc., etc. So you can actually take a look at this stuff on a networking device. So what about the verbs? So we have buffer, we have queue, we have cache or cache. And so now let's turn them into verbs. So we're buffering or we're queuing, etc., etc. And that really is just the process of moving things in and out of this particular kind of memory. And again, it doesn't really matter what kind of technology you're actually talking about. Are you programming? Are you doing application development? Are we talking about operating system? Are we talking about a network device? Are we talking about a computer that's receiving things? Are we talking about a modem or an access point or a switch or a router? It doesn't really matter. We have queues or buffers everywhere, and they all have to deal with the same kind of activity. Before we get to the next couple of ideas, let's remember that we've got three things that we're trying to deal with when we're talking about the network. Now, when you're on a machine, you have the same sort of issues. It's really, you're trying to move things as fast as possible internally. But as a network kind of guy, as a network plumber, I am very concerned with what's going across a network. And for me, those big three are latency, jitter, and packet loss. Now, jitter, especially for real-time applications, can be a real bugaboo. It is the difference between expected and actual arrival time. So if you're expecting a packet, pow, 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 but you get them, pow, 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 pow. That variation in arrival time leads to differences in performance or experience. And so the quality can vary over time. So what do? Well, if we buffer traffic, that means that when you're starting to watch a movie, the movie doesn't play when the very first packet or frame gets to you. We buffer, very commonly, a couple of seconds, right? 8 seconds is the number that we use a lot. You buffer a couple of seconds and then it starts to play. So that when you're watching the movie, we're pulling things in and out of a very local buffer, and we're playing them, and you get a consistent experience no matter what's happening on the network. So things can arrive at various times, but because you've got that buffer, you have plenty of time to even out the jitter behavior. Latency is the #1 cause of poor perceived call quality in voice over IP systems. But of course, latency causes all kinds of problems for video, for two-way communication, for gaming, lag, death, all of those kinds of things, right? So latency is a real enemy, and there are lots and lots of sources of latency. Every single device that touches packets or touches the data flow creates or causes latency. And packet loss is the death of TCP connections. This is why real-time applications very commonly use UDP instead of TCP, because TCP is the mother hen, right? It says, I lost something, can I have it back? I want to straighten out my byte flow. And uh, in that delay, what you're doing is destroying application performance. So packet loss is a real problem. So we try to keep latency to a minimum. We try to keep jitter to less than 5 milliseconds, and we want less than 1% packet loss. Otherwise, it's almost not worth doing whatever you're doing. So what is buffer bloat? Our friends out at bufferbloat.net tell us that buffer bloat is the undesirable latency that comes from a router or other network equipment buffering too much data. So the fun thing about this is, as they say here, ironically, this is created by previously attempts to make it, meaning your connection, work better. We're trying to combat latency, packet loss, and jitter. We're going to use buffers, common approach. But too much buffering creates additional latency in the connection. So essentially, buffer bloat is too much buffering along the pathway at some point. And this comes as an outgrowth of our speedy networks. I'll be quick about this. Historically, we've had lots and lots of defense or lots and lots of strategy for handling connections. TCP, for example, had a window size of 65,000 bytes. And right in the RFC, it says, be conservative in what you send and liberal in what you accept, right? Be a good net citizen. Don't dump a lot of stuff into the network. Queuing or buffering to handle latency, packet loss, and jitter issues was a perfectly valid approach to this. And then, of course, we used to have error-prone networks. Lots and lots of single and multi-bit, but especially single-bit errors going across the network. Well, today our networks don't have as many errors as they used to. And because we're sending so much data, the window size is completely inappropriate. So we introduced window scaling factor to make a TCP sliding window have a much larger capacity. So buffer bloat may be one of those things that, we're moving things pretty fast. Memory is better, processing is better, and if somebody along the pathway is still clinging to, giant buffers, maybe they're creating a problem. Maybe let's just put in or acknowledge that we have much faster, much higher processing networks, and we should be able to forward things much, much faster without so much buffering. As an example, in my own network, I recently changed my internet connection over to fiber, and so I had literally nearly a 100 times increase in upload speed, not download speed. Download speed was almost 10 times, but upload speed was 100 times faster. Now, one fun thing about bufferbloat.net is they offer links to buffer bloat tests. And I got a grade of D on the test that I ran for this video. Now, I was wireless at the time. I didn't do a wired test, but just for fun, go out and give that a whirl and see how your network survives. Another one that you should be aware of is speed tests, right? So you can see what your upload and download speeds are. And since we've been talking about iPerf has lots of parameters that allow you to mess around with the buffers and see what works on your network and see what changes to the buffers due to the tests. So some examples of options are size or when to transmit, when to clear out the buffer. And we couldn't have a conversation about buffer thingies without talking about buffer overflow. So we've got a couple of definitions here from Cloudflare and the Open Worldwide Application Security Project. Buffer overflow is an anomaly that occurs when software writing data to a buffer overflows the buffer's capacity. So if you define a memory location as needing this much space, but something is written there that overwrites that buffer and writes into the next memory location, that's a buffer overflow. In other words, too much information is being passed to a container that does not have enough space. And that information ends up replacing data in the adjacent container or memory location. And so the graphic up there also comes to us from Cloudflare. So that's what happens. So the definition from OWASP there, buffer overflow errors are characterized by the overwriting of memory fragments of the process, which should never have been modified intentionally or unintentionally. It causes exceptions, segmentation faults, and other errors to occur, which leads to undefined or unexpected results, right? We have no idea what's going on. And the key question then is what got put in the overflow and what happens with it? So your program might be addressing, in this case, the first 8 bytes, but something that shouldn't have been in there got put in the other buffer and might get executed, might get read, and cause difficulties with your process or even other processes. Now, I thought it was also fun in spending a little bit of time with this for this video on Stack Overflow. There are folks asking the question, what is a buffer flow and how do I cause one? Now, I'm sure it's benign, right? They're just doing their own testing in whatever programming language, but I thought that was kind of funny. All right, so this has been a little time with buffer thingies. We went over memory and caches and queues and buffers. And don't forget our latency, packet loss, and jitter. Oh my. And of course, we touched on buffer bloat and buffer overflow. One is an attack or potentially an attack. Now, a lot of buffer overflow happens unintentionally, but certainly bad guys, nefarious actors can take advantage of buffer overflow problems. Buffer bloat is something that's we probably shouldn't have as much as we do, but there we have it. Hey, like and subscribe as soon as you're done buffering, and no matter what kind of buffers you're traversing on your way to this video, may your packets always reach their destinations, even if they're a little late.